So I want to talk today about amino acids. Follow along in your topic booklet at home. Amino acids are a special category of compound. As the name suggests, amino acids have two functional groups. There's an acid group on one end, carboxylic acid group on one end, and an amine group on the other, amino acid. We are going to be solely interested in amino acids where the amine group and the acid group are attached to the same carbon. Of course, technically any molecule where you have amine and carboxylic acid somewhere in the molecule are amino acids, but we're going to be particularly focused on these. If I put a hydrogen on there, it doesn't have to be a hydrogen, but let's assume it is for the moment, and then change the R group down here, I have an option to make a whole bunch of different amino acids. So the simplest possible amino acid would be with a hydrogen on there. That's called glycine. But if I swap that and put a CH3 on there, then that makes a new amino acid. That's called alanine. We should probably give them their IUPAC names. Can you just write down the IUPAC names for these two amino acids? Stop the video and I'll come back in a moment. So the carboxylic acid is the more important functional group. So NH2 is going to be amino something. We've got ethanoic acid here, and the amine group is on carbon 2, although actually it can't be anywhere else. So amino ethanoic acid, or 2-amino ethanoic acid if you want. For this one, we've now got 3 carbons in the carbon chain, so 2-amino propanoic acid, and we definitely need the 2 now because the amine could be on carbon 2 or carbon 3. Okay, so there's lots of amino acids. You're not going to be expected to know the structures. These are the ones I've just pulled off the data sheet, so you get these in the A-level exam anyway. And you can see they've got various names, and they differ by the R group. So we've got a CH3, and we've got another carboxylic acid there. We've got a sulfur hydrogen group there called a thiol. Long carbon chain with an amine on the end of it. Benzene ring, of course, and then just an OH there. So the different amino acids have slightly different properties, but they're all capable of doing the same basic reactions. So for starters, they will all react with acid because they've all got an amine group. So anything with an amine group, I'm just going to use an R there to generalize it. Anything with an amine group on it, when it's put into an acid solution or a low pH solution, is going to protonate the nitrogen. And then, of course, similarly, because I've got an acid group on the other end, they'll all react with base. So if I put my amino acid into a solution with high pH, or a solution of hydroxide ions, sodium hydroxide, something like that, then we're going to deprotonate the acid. So it probably makes sense to think, well, hang on, if at low pH we protonate the base, and if at high pH we deprotonate the acid, there must be an intermediate pH where it does both, and that's true. You might think, okay, that pH has to be 7, but it doesn't. partly because the amino acids themselves, the R groups, can contain bases or acids, but they all, each amino acid has its own sort of little middle point where it will do this. So the amine and the acid will react with each other. I'm just going to put a reversible arrow on there and form this weird chappy here. So it deprotonates and protonates itself, and it's called the zwitterion. So the zwitterion is a weird molecule because it has charges, so it's like an ionic compound almost. And when amino acids turned into solids, they actually form a solid as a zwitterion, which means you've got negative and positive charges attracting, so the melting points are much higher than you'd expect for a fairly small, simple molecule held together by intermolecular forces. It's held together by charges, and that gives it a much higher melting point. Just before I go on there, just a note, I'll just do this over here, that most of the amino acids, not glycine, but most of the amino acids have 4 different groups around a carbon. Let's just call that R. So of course are therefore capable of forming 2 different structures that are mirror images of each other, which are of course optical isomers. What's interesting, I think, about the optical isomers is nature produces only one of the versions of each amino acid. They're only ever found as one isomer. According to my PowerPoint, apart from some exotic sea-dwelling cone snails. There we are. I don't know where I got that fact from, but yeah, might want to Google that. So there we are. That's the same structure there. And that's the zwitterion. As well as forming zwitterions, which is a unique chemical reaction for amino acids, of course, amino acids react in the same way as amines would, and in the same way as carboxylic acids would, because they have an amine group and a carboxylic acid group. And one of the wonderful things about organic chemistry is we don't have to worry about the other functional groups in the molecule. If an amine is doing its amine thing and reacting like an amine, you can ignore all the other functional groups because they probably behave in a different way. So there are 3 reactions on the board there. I'm just going to step away, pause the video now, and have a go at writing down the products of those 3. There, I've just transferred them to the board, if that makes them easier to see. Okay, so this is where an extensive knowledge of organic reaction chemistry comes in handy. So we have to remember that methanol, in the presence of a carboxylic acid and conch sulfuric, will react to make an ester. So the rest of the molecule stays the same, and we make the ester COCH3, the methyl ester of the carboxylic acid. In the presence of a strong base, like sodium hydroxide, the acid will deprotonate, but be careful, there's another acid down there, and we're told the base is in excess, so that will deprotonate as well. The amine will react with an acid chloride to make an amide, which I just need a bit more room there. that will form that, and then the rest of the amino acid will stay the same. There. Okay, there's another set of reactions there on the board for you. Have a go at those. Just pause the video now and have a go at writing the products of those. So this first one, we've got HCl, which is going to react with the amine to make N+. But again, the HCl is in excess, so that is also going to protonate the other nitrogen in the R group. Reacting with bromomethane, well, bromomethane gets attacked by nucleophilic substitution by the lone pair on the nitrogen. So it's going to make, I'll just move this, there we go. Put it over here, CH3PR, there we go. It's going to make substituted amine there, and then the rest of the molecule will stay the same, doesn't affect the benzene ring. And then lastly, my carboxylic acid with consulfuric will react with the alcohol in the R group. Don't forget the R group, that can react as well. To make a new ester where the alcohol oxygen goes first there, and then I would have the ethanoic acid part of the ester there. I suppose it could conceivably as well react with the amine, so we should probably just cover our bases. I'm guessing the mark scheme would have both of these structures in if this question was asked in an exam. Sorry, why have I put I've got all that wrong, haven't I? Forgot my nitrogen. Okay, there we are. So there's the new amide, then we have the CH, then we have the COH. There we go. And that comes off there. Or I guess if the acid was in excess, you could put both on. Why not? Okay. Well, this last reaction here begs the question: if an acid can react with the amine to make a new amide, then surely the amino acid can react with itself, which is something we saw in the polymers module. And I seem to remember saying something along the lines of, you probably don't want a molecule in a bottle that reacts with itself, because you're going to come back 6 months later and the molecule would have reacted, and instead of having a bottle of liquid, you're going to have a bottle of solid polymer. Well, amino acids are not so reactive. You can have a bottle of amino acid and it won't react. Amines are a little bit less reactive than alcohols. Oh, let's see, sorry. If I just call this R1 and R2, there we go, that's fine. So I've got my 1 and my 2 in the wrong place, because otherwise it looks like I've got 2 R's. Right, if I react those two together, we could imagine that the H there and the OH there would react and remove water, and so we'd have our new amide group there, R2, R1, I'd still have an amine on the end there, and I'd still have a carboxylic acid on the end there. So this functional group here, we would of course call an amide. Biologists, for their own reasons, I'm sure, call this a peptide bond or a peptide linkage. So the amino acids are joined together by the peptide or amide. You can call it either in the exam, they don't mind. And that joins the two amino acids together. So the question I've put on the sheet there is, draw me a dipeptide formed by serine and alanine. So alanine just has a CH3 there, and serine has an OH on there like that. So if you could just pause the video and draw me a dipeptide formed by alanine and serine. So yeah, if I join these two together, so we've got a CH3 there, there's my new peptide link, and then I've got a CH2OH there. But that's not the only peptide, dipeptide, I should use that. Di, of course, because we've got two amino acids. That's not the only dipeptide I can make from those two amino acids. I could swap them around and have the serine on the left. There's my peptide linkage. Sorry, I've already done that. I'm looking for an H there. See, and there are the alanine on the right. So just with two amino acids forming a dipeptide, we've already got two possibilities. If I had three amino acids, then I could make, how many is that? 6 different tripeptides, not including, of course, ones that would be, you know, alanine, 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 and so on. Very quickly, we can make lots and lots of tripeptides, oligopeptides, polypeptides. There are 21 naturally occurring amino acids, so that's going to get out of control very quickly. When we're looking at polypeptides, there are millions of different combinations of ways of attaching 21 different amino acids. Think letters in the alphabet. Think how many words you can make, and most of the words we use are pretty short. Amino acids will join together in the hundreds. If you have hundreds of amino acids, the number of combinations, permutations, is mind-boggling. So these polypeptide chains then can coil up in special ways and form sort of magical molecules, really, called proteins.